In our last lab, we used the titration with a burette and phenolphthalein to determine the concentration of acetic acid in vinegar. Sometimes you will use an indicator such as phenolphthalein, but sometimes a titration curve is more useful. So what is the relationship between a titration curve and the endpoint we find with our phenolphthalein indicator? This setup includes in the beaker vinegar and 20 milliliters of water plus the phenolphthalein so we can see what happens, and in the burette the same sodium hydroxide solution that we standardized during the last lab. The other device here is a pH probe, and it's going to take the pH, which is the negative log of the concentration of the hydronium ions in the solution. We also have a stir bar in here and a stir plate so that if we wanted to have it mixing, we could. For the moment, because the liquid level is so low, we will be mixing by hand. To make the titration curve, I will record several points where I have added a certain amount of the sodium hydroxide solution and the pH. So my original volume on the burette was 19.22 milliliters, and I had a pH of 2.81, and then my second increment caused the pH to rise to 4.09. So the burette reading was about 24.2, but this is only 5 milliliters added. So we're going to see what happens after we add several increments of 5 milliliters. At this point, I've added almost 20 milliliters, and you can see the solution is still colorless and clear. And you can see my data points on the graph here. The initial data point at 2.81 is where the no sodium hydroxide was added, and we can see that the pH is increasing, which makes sense because the sodium hydroxide is a base. And you'll notice that at first the pH rose quite sharply from 2.81 to just a little bit over 4, but with each addition of the sodium hydroxide, the pH change seems to be leveling off just a little bit, and so I'm not seeing those huge jumps. This means that we are in the buffering region of this particular acid. And so buffering will be talked about at a later date, but as we get closer to the endpoint, we want to keep adding smaller amounts because we're going to see the pH start to change more rapidly again. So now I'm going to add in 1 or 2 milliliter increments. You can see that the pH is starting to rise more sharply here. Also, when I swirl the liquid after adding my sodium hydroxide, the pink color is lasting a little bit longer. So during our standardization lab, this was the point where we wanted to add things just a few drops at a time, and that's what I'm going to do here, just adding a few drops and then keeping a record of the pH. At this point, I'm only adding a few drops of sodium hydroxide at a time. I'm trying to keep it so that the increase in the pH is about 0.2 or 0.3 each time, and you can see that the pH is rapidly increasing. Now keep in mind that the pH is increasing because of the logarithmic scale that we are using that determines how quickly it is rising, and because we're approaching the equivalence point. It's not because of the small additions that it's rising quickly, but rather because of where we are in the titration, so close to the end point. I've added 4 drops, and I think this is going to be the point where I reach the end point or the equivalence point, and we're going to see that the color of the pink is going to stay. The reason that I know that this is close to the end point is that if I look at my pH, I'm at 7.15. Now this is before I've mixed everything, so let's see how this works. And as this all blends, we can see that that pink color is staying. So this is what we would call the end point of our titration if we were just using the phenolphthalein. Now let's look back at our pH. It is 8.42, and look how dramatically that pH has gone up, even though we just added a few drops, a few tenths of a milliliter in order to increase this much. Now what's going to happen is something a little bit unusual. It's going to continue to rise for a bit and then it's going to flatten off again. So let's keep adding a few drops at a time and then we'll start increasing the amounts. You can tell by the pink color here that we're well past the end point of our titration, and yet I've only added a few tenths of a milliliters more than our equivalence point or end point would have indicated. This is why the indicator, it's important that the indicator be the faintest possible color that we can still observe and hold steady within the flask, because darker colors aren't going to change very much, and you'll see that as we add some more volume of sodium hydroxide. I've continued to add just a few drops at a time, and you can tell that while the color's a little darker, it hasn't changed a whole lot. Now if we look at our graph, notice that instead of continuing to rise very sharply, it's starting to bend over again. It's starting to have less and less of a slope. And so we're going to see very soon it's going to level out quite a bit. So this is the final color of our solution, and this is the final titration curve. We're not going to add any more because I've run out of readable lines on the burette, but theoretically we would keep going and the pH wouldn't continue to rise too much more with each addition. So the important features of this graph are going to be the relatively flat area near the beginning, and that's called the buffering zone, and then the more vertical area as we are going almost straight up, and that is where we find our equivalence point. That one is significant because while we change the volume very, very little, the pH is changing a lot, and we're more interested in the volume than we are in the pH. So whether I pick a point near the beginning of this vertical area or near the end of this vertical area, the volume that I'm looking at is going to be very nearly the same. And so that's an area where I'm not going to be able to make too much error depending on how far right or left I go. And so all of those are going to be fitting in pretty tightly. Now your lab directions will give you some specific ways of determining exactly where you want to choose that volume. Acetic acid is what we call a monoprotic acid. That means there's only one hydrogen ion per acetic acid molecule that can dissociate from the acetic acid and become a hydronium ion in the water. And so there's only going to be one place on this curve where it rises sharply. This week's lab, you're going to be looking at some diprotic acids. These are acids that have two acidic hydrogens, two hydrogens that can be dissociated from the acid molecule and taken up into the water. And so the curve is going to look a little bit different. It's going to look like two of these curves sort of stacked on top of each other. Now it would be wonderful if they were nice and neat like this curve is, but what we're going to see is that it isn't always easy to tell where that rise is, because when we have a diprotic acid, the rise isn't going to be quite as much, the change in pH isn't going to be quite as much, and so we've got a much smaller area vertically to tell where the pH is rising rapidly. So now for the buffering region. The buffering region changes quite dramatically in the amount of NaOH that we've added, but the pH doesn't change a lot. So we're going to use this for a pH that we're interested in. So this region is going to help us find what is called the Ka, or the equilibrium constant for acids for a particular compound. So it turns out that if we look at where the equivalence point is on our graph, which I will try and illustrate here, which was roughly at our 43.38 milliliters, and we go halfway back. Well, halfway back, remember, is halfway between that point and where we started, and we started close to 19. The relationship between the graph and the Ka value is shown here. We know that the equilibrium constant is the products H plus and the conjugate base A minus over the reactants, HA. For the reaction HA, this is our acid in equilibrium with those products. We can break this up into Ka being equal to H plus times A minus over HA. If we take the negative log of each side, we will have the pKa on the left-hand side and the pH, and the log of HA over A minus. If you want to look at how we derived these logs, you can look on the right-hand side. But the long and the short of it is that we have the log of the acid over its conjugate base. And when those two things are equal, we're at 50% dissociation. We're also at 50% of the equivalence volume. When those two things are equal, that means you have the log of 1, and the log of 1 is equal to 0. So the pH plus 0 is going to be equal to the pKa, or the pKa is equal to pH. What this means is that you can find the value of pKa by looking at the pH at half the volume of the volume at the equivalence point.